Well, it's great to be here. Thanks for sticking around till the very end. So what I want to talk about today is a subject that I've actually never spoken about before, although my work has probably touched on it, which is this subject of the conference of big data and really sort of trying to think a little bit about what do we mean by that and how is it useful for doing social science, particularly on the web. And so I want to start by sort of saying a little bit about why I find social science interesting. I certainly don't speak for all sociologists here, because sociologists see the world in many, many different ways. But when I think about sociology and why I got interested in it, I view social phenomena through the lens of what sociologists call the micro-macro problem. This idea that the things that sociologists and other kinds of social scientists study are intrinsically macro-level phenomena, things that are kind of social entities, firms, markets, cultures, etc. And at some level, we know that, that all of these entities are really comprised of individual people who are, who take actions, who have beliefs, preferences, and are actually doing everything. And yet, we still speak and think in terms of these collective entities, right? So we still sort of, we want to understand how firms work, and we want to understand that in a way that isn't just at the level of individual people doing things in their everyday lives. And the question of how you get from the micro level of individuals to the macro level of the social world is, I think, maybe sort of the core intellectual problem of social science. It's also an extremely difficult problem, and one that I don't think we have really even gotten close to cracking. Wherever we have encountered it outside of the social sciences, it has also turned out to be an extremely difficult problem. So, in the other sciences, this same problem is usually referred to as emergence, and we encounter it in physics, we encounter it in biology, we encounter it all over the place, and as we've sort of learned over the last few decades, this is sort of where all the really hard problems lie. So why are they hard? Well, empirically, it's very difficult to study these sorts of problems because you have to be able to observe things at multiple scales at the same time. So you have to be able to, in the social world, maybe study, millions or hundreds of millions of individuals, and also how they interact, and also what they're behaving like, and also how they're doing all of this over extended periods of time. And the sort of burden of collecting that kind of data is extraordinarily high. Also, it's very difficult to do experiments, right? Even sort of any sort of controlled environment is extremely difficult to replicate in the social world. And not only is it impractical, but it's often also unethical, right? It'd be nice if we, from a scientific point of view, it'd be nice if we could randomly assign students to schools and see whether private schools really do a better job of educating kids than public schools. We'd like to get rid of the endogeneity effect, but that would be grossly unethical, so we can't actually do that. And so we're kind of stuck in the social world with a situation where we can't observe most of what we would like to observe, and we can't do experiments most of the time, and it's very hard to do science under those conditions. So with that as a sort of historical background, what I find so exciting about the last decade or so, with the explosion of the internet and the web, is that some of these historical constraints are being lifted. And as many people have observed in the last couple of days, both the scale and also the scope of the data that we are able to measure or record has increased dramatically, and also the cost of acquiring it and the speed with which we can acquire it, and the speed with which we can, or our ability to replicate studies is also increasing. So I'll try to sort of parse out some of these things throughout the rest of the talk. So how is all of this relevant to social science? Well, there are, I think, a couple of ways in which we might think the bigness of the data is. Has anyone actually, I sort of came in late today, has anyone sort of defined what they mean by big? I'm never quite sure when data actually gets big. In 1974, a conference was created called the Very Large Database Conference, right? So this is now called VLDB. So, I don't know if big data is bigger than very large data, but I'm quite confident that what is big now will not be considered big a few years from now. So there's a little bit of of a moving target. But I do think there are some sort of concrete issues that arise, in particular, given any sort of technological state of computing, at some point the data gets large enough that you have to develop special methods to be able to handle it. And so a lot of work now with very large-scale data analysis relies on sort of parallel computational frameworks like MapReduce, simply because you can't store the data in a single machine, right? So there's sort of fundamental limits that we're starting to bump up against in terms of, even as computing power is increasing dramatically, the size of the data sets that we're dealing with is increasing even more dramatically. And so we have to start being sort of inventive about the technology that we're using, and also the computer scientific skills that are required to deal with it. But quite apart from these sort of technological and technical issues, I think another, and to me more, personally more interesting phenomenon is that the scale, and also I would say the granularity of the data, the fact that we can observe very, very large populations at the individual level, to me allows us to start looking at old questions, and many of the questions I'll talk about today are in fact very old questions in a new way. And so here, big actually means something rather different. It's not sort of dependent on the state of the technology and what it's capable of processing in a reasonable amount of time, but really it's relative to the size and type of data that has been available historically. And so, in some cases, even having a few thousand observations when it comes to, say, lab experiments, that's a very big number for lab experiments. It's not big in terms of the analysis challenges, but it's big enough that you can still start to ask new questions. And so that's sort of what I'm going to focus on in this talk, and I won't really touch on the technical issues. Now, obviously, both of these things can apply at the same time, but I want to separate them because neither of them necessarily implies the other. You can have a huge amount of data and still ask a very uninteresting question of it. You can also answer very interesting questions with data that's sort of not big in this sense. Okay, so for the rest of the talk, I want to really draw a contrast between two different types of studies that I've been involved with over the last several years. One is observational studies. I'd say that this probably characterizes most of the talks that I've seen today, where we're looking at data that is kind of out there in the world that's been generated by various kinds of internet and web platforms, and we're trying to learn something interesting from it. And I want to contrast that with experimental data, which is another interesting trend that has been sort of gathering momentum in the last several years, where we're sort of increasingly able to simulate lab-like environments online and run sort of controlled experiments, and also, even more recently than that, these very large-scale field experiments that I'll just sort of touch on at the end. So I'll talk a little bit about the pros and cons of each type of data. I'll give some examples. I apologize in advance that I will be sort of rushing over the details, so please don't get frustrated if you're trying to understand exactly how things were done. I'd be happy to share the publications with you afterwards if that's the case. And then finally, I'll sort of conclude with some hand-waving speculations about things that might happen in the near future. So to start with observational data, this is when we think about big data, this is really what we're thinking of most of the time. And it's easy to see why if you look at a site like Facebook, rapidly approaching the 1 billion mark in terms of the number of people. If you think about a site like Twitter, it's generating, it's not quite that many people involved with Twitter, but there's certainly billions of tweets in a given year, so there's enormous scale to some of this data. It's extremely cheap to collect. In fact, for researchers, it's in a sense free to collect because it's already been collected for other purposes. And it has sort of an advantage that in some sense you're really studying the real world, right? I mean, there are certainly people who are even crankier than I am who think that, that anything that's online is somehow not real. I think that history will be unkind to those people, that in fact we are seeing more and more very real activity migrating online. So I think that to some extent a lot of this data is actually studying real behavior. And of course it increasingly allows us to sort of replicate our studies over and over again, which is a nice feature. But it's not perfect. Observational data is problematic in that it's very difficult to tease out causality, as we're starting to, I mean, we've sort of in some sense always known this, but we keep getting reminded of it, that you want to identify, you see correlations in your data and you want to impute meaning to those things, but that is extremely tricky. And again, when the data becomes extremely large and everything becomes statistically significant, it's easier and easier to fool yourself into thinking that you're seeing something that you're not. Another related problem is, again, because this data is often, almost always being generated for some reason other than the research question that you bring to it, it's often not necessarily well suited to that research question. You may, you want to understand or map out social networks, but really what you can measure is email exchange, and then you can convince yourself that one is a mapping of the other, but you're never quite sure about this ground truth. And so it's often problematic to interpret a lot of this data. And of course, there's all sorts of biases associated with the user interface, or the population that's using a particular platform, or the language. Some of the questions that came up today that have potentially very large biases, or result in potentially very large biases, and we really have no way to know what they are. And then finally, of course, as many people are talking about these days, there's all sorts of interesting and potentially problematic privacy concerns. So lots of interesting positives and some negatives about this observational data. Just to work through a recent example, one of that I think illustrates sort of how new types of data can shed new light on an old question. One thing that we've been working on in our lab recently is trying to use online data to understand diffusion. So, of course, this is the study of adoption processes is a very old one in marketing science and in sociology, going back well before. I mean, so Ryan and Gross is sort of back in the 1920s now. So we're coming up on several decades of work on diffusion processes. And when we think about diffusion processes, we're really sort of trying to model some individual level process where some person learns from or coordinates with another person, right? So there's sort of copying processes, there's learning processes, there's coordination processes. And all of these can be sort of imitated by some kind of viral mechanism. Right? So if we think about the analogy that we use informally, and in fact even formally in a variety of models, is to think about the spread of some infectious disease, and you imagine that an idea or a product can spread from person to person in the same way that a disease does. So back in the 1960s, Bass really literally took a pre-existing model of infectious disease and used it as a model of new product adoption. Since then, there's been a sort of wide variety of related models have been proposed: threshold models, learning models, cascade models. I don't know how many models we have of diffusion. It's certainly dozens. It might be hundreds. There are thousands of papers. There's almost no data, right? So there's sort of a interesting kind of model to data ratio problem in this literature. But intuitively, and what is being captured by many of these models is something like this. When we think about word of mouth diffusion, or we think about things going viral, this is the kind of image that we have in our minds, where something starts off at some originating node here or here, and then it spreads out through many generations of individuals contacting other individuals and infecting them. And over some period of time, this process reaches a large number of people. So we want to understand how things can spread to become large through this multi-step peer-to-peer process. Now, the problem is that historically the data that we've had looks more like this, right? And so this is the famous Coleman, Katz, and Menzel paper on the diffusion of tetracycline among physicians in the Midwest. This is from Bass's seminal paper in 1969, and this is sales of black and white televisions, right? So it really dates it. And so what these curves are aggregate level data. So this is the number of devices or the number of prescriptions that are being adopted over a whole population. So there's nothing in here about the actual person-to-person mechanism. We just see this evidence at the aggregate level. And of course, these curves are consistent with the sorts of diffusion models that people have studied, but they're also consistent with lots of other kinds of models, right? So they're consistent with models that just assume people are heterogeneous and they adopt at different times. They're consistent with marketing efforts. So it's sort of very hard to calibrate or reject models based on this aggregate level data. The other problem with the kind of diffusion data that we've historically had to work with is that you really only see things when they diffuse successfully, right? If a product doesn't diffuse through a population, nobody ever thinks to go out there and understand what happened, right? Because nobody ever notices it. So there's a sort of sampling on the, or selection on the dependent variable problem going on, that we only tend to study successful diffusion, whereas the models certainly are capable of predicting instances where diffusion does not fail and arguably does not succeed, and arguably, in fact, most attempts at diffusion fail, and we'll see that in a moment. So ideally what we would like, if we want to really study, apply data to the model mechanisms themselves, is data that is at an individual level, and so we can see individual level person-to-person diffusion, and we would like to have a total sample in the sense that we want to see everything, every attempt at diffusion, so we can understand exactly when do things diffuse and when they don't. Now this is something, of course, that is criteria that are well satisfied, at least in some instances, by diffusion that happens online, and there's been a bunch of papers written in the last several years that try to map out diffusion patterns. And so what we wanted to do in this project is to ask a related question, which is, when you look at all of these patterns, how much of it actually seems to be viral? So how much diffusion out there in the world, how much adoption out there in the world is accounted for by these sorts of diffusion processes versus some other process? And when you do see viral diffusion, what does it actually look like? Can we sort of formalize that concept and see what the diversity of possibilities is? So this is the first. I'm going to describe two projects, one of which is published. The other one is literally ongoing work. I've been exchanging emails with my intern today to try to get the updated results. So this is not even hot off the press. This is actually still in the oven, and as a result, it may be a little half-baked. But a couple of years ago, my colleagues Sharad Goyal and Dan Goldstein and I worked on this diffusion project where we took 6 unrelated, previously worked on projects that had been conducted over the past few years, all of which were in some sense designed to go viral. So we had so Dan had worked on this. He's a psychologist, and he had launched this online game called the Secretary Game, which is a decision making problem, an optimal decision making problem. And there was a social sharing component to this game, and so he had all this data that he had collected about how people had passed this game along to their friends to have them play it as well. We helped, this was work when we were back at Yahoo. We had helped the Yahoo for Good people build a campaign that they called Ripples of Kindness, where people had to do something nice for somebody else, and then they had to tweet about it or post a status update and get their friends to do something nice. So a sort of pay it forward kind of model. And they wanted us to look at the data that had been generated by that campaign to see how far these ripples had actually spread. A third application was this synchronous video watching app that was built by our colleague Elizabeth Churchill at Yahoo Research. So this is an app where people can actually watch a video at the same time, and they can chat to each other, and they can pause the video, and the video is synchronized between the two of them. And again, there's a social sharing component built into this, because obviously you don't, it's only synchronous if you have someone to watch it with, so you have to share this with your friends. So all of these have a nice feature that we can actually directly observe who passed a link to whom. So we know exactly how things diffused. For the other three examples, we have to infer it because we have the underlying network and we can see how things have spread over them, but we have a little bit of a homophily influence problem, but I don't think it's too serious. So here, the first example is a premium IM service that Yahoo launched several years ago called Yahoo Voice. And so again, you have this, it allows you to make phone calls from your instant messaging service. And this is something that people had to pay for, so it's a relatively costly thing to adopt. But of course, once again, you want your friends to be using this, so it's a social thing. FriendSense is an application that Sharad and Winter Mason and I built a few years ago, where we were interested in how people's political beliefs were similar or dissimilar to their friends. So again, it's an application where you actively want to recruit your friends to play it so that you can compare yourself to them, see how well you know them. And finally, we had done a previous work with Eitan Bakshi, who was an intern of ours now at Facebook, trying to predict influence on Twitter. So the point I want to make is that these 6 examples are all very different. But they're different networks, there are different adoption processes, there's different costs involved. There's sort of an enormous diversity across these different applications in terms of what you might think will be going on. And so what I want to emphasize then is that when we look at the diffusion patterns across all of these applications, we see sort of tremendous, striking similarity. And it's not the kind of similarity that you might expect. So the first result that we get is almost nothing spreads. Okay, so everything is, you can see these are all highly skewed distributions, but the point here is that, is summarized here, that, 96 to 99% across these different applications of these diffusion trees. So if we sort of back off to look at something like this, this is many generations deep. What we are seeing is that everything is within one generation of the seed node. So nothing really looks like that. But you might think, okay, well that's fine. There are, we know that many natural phenomena are scale-free. What we care about is this stuff in the tail, because that's where all the really big things are. So even if the big events are rare, that's okay, because they still account for most of the action. But what we found is actually an even stronger result, that if you, instead of looking at the trees, if you look at adoptions and you say, what percentage of all adoptions, like everything that we record, what percentage of all adoptions occur within one step of one degree of the seed node, it's still the case that almost all adoptions are not viral. Right? So another way to make this more concrete is to sort of show you the actual motifs. Right? So each one of these figures represents an adoption. So this is an instance where somebody adopts and nobody follows them. They recruit 0 people. This is an instance where you adopt and then one of your friends adopt and then it stops. Right? So you can now sort of interpret all of these all of these different motifs, and you can see that the vast majority of them are accounted for by just a handful of these very simple structures, only two of which, these two here, and you see another one, you see them repeated down here again, have more than depth 1. So there's essentially no viral diffusion happening here at all. So summarizing even further, if instead of all of these models that I showed you before, you said, look, I have a very simple model of diffusion. 90% of the time, nothing happens. And then 5% of the time, this happens. One of your friends adopts. And about 1% of the time, 2 of your friends adopt. And then some other stuff happens, right? About 1% of the time. That completely stupid model would account for about 99% of everything that you see, okay, for all adoptions. So this is sort of very far from, and I say this as someone who has written a number of papers on modeling diffusion and trying to understand how big events occur and when things go supercritical and you get these massive cascades. I have published these papers myself, and so it's a little discouraging to see that most of what actually happens in the world doesn't look like any of that. Still, you might say, okay, fine, but I don't care. I still want to know what the big events look like because that's what I'm interested in. And so we are also interested in that. We want to actually delve into this tiny little bar here and see if some weird stuff is happening. And so in the last summer, Sharad and Jake Hoffman, another one of my colleagues at Microsoft, and Ashton Anderson, who's a brilliant grad student at Stanford and was an intern with us this summer, have really, really been looking hard for these things. Okay, so we have, so this is you want big data. This is big data. Okay, so this is every link in 12 months of Twitter data. Every tweet that contains a link to a video, a news story, an image, or a petition. So we have the whole fire hose, we have everything, and we have a few 100 million observations in total. And then we throw out everything except for the stuff that's really popular. So we now want to restrict attention to the content that has at least 1,000 adoptions, that at least 1,000 people have linked to a particular story or who have posted or tweeted about a particular video. So we only want to study the stuff that's popular. And in the case of news, that's about 3,000 URLs, distinct URLs. And for videos and images, it's about 10 times that. So we have we're reducing from hundreds of millions to a few tens of thousands, but we still, even that is still quite a lot of data. In addition, we have crawled the entire active follower graph of Twitter. So this is anybody in that year who tweeted anything, or any one of these tweets. Not any tweet at all, but anyone with a link to a video, a news story, an image, or a petition. And that constitutes about 65 million users with about 10 billion edges. Now we're not done yet. We're still crawling it, but that's our sort of rough guess of how big it's going to be when we're finished. So what are we going to do with all of this data? Well, basically what we want to make is a distinction, a structural distinction. Right? So we're looking at large events, but going back to my comments earlier about the aggregate data and how things can spread. There are very different ways in which things can get large. So I think that we would all agree that this looks pretty viral. I hope that we would all agree that these things do not look viral. These things are big. They've resulted in a large number of adoptions. In fact, probably more adoptions than we have over here. But they're pretty much all dominated by a single node that has, it's probably like a news organization. It's like the New York Times or something, and then it broadcasts out a story, and then it gets a bunch of retweets, and it doesn't really spread, right? So this is big, but not viral. And we would like to be able to differentiate between these two sorts of spreading processes. And so what we need is a notion of what we call structural virality, right? So this is sort of somewhat different from the usual parameters that we have in our heads when we talk about models of viral spread. So typically in a BAS-style model or an SIR model, you think about the infectiousness, you think about the contact rate, you think about these other kinds of the refractory period. These are all the sorts of parameters that you think matter to viral spread. Just imagine you run one of these processes on a network, something happens, you get a result, you get an actual pattern, you get something that looks like one of these things, and you want to be able to characterize, quantify the structure of these events. And so we came up with a bunch of different definitions, or rather I should say Sherrod came up with a bunch of different definitions. And it turns out they're all sort of highly correlated, and they all capture very similar patterns. So what I'm going to talk about is this one here, which is known in modern network terms as average path lengths. It's the average number of links between any node and any other node. It turns out that this was a metric that was invented by Weiner back in 1947 in the context of molecules. This is published in a chemistry journal. So we ended up studying the Weiner index. And so we can ask, once we have this measure of structural virality, we can look at the kinds of the different types of events that we see. We can try to characterize their diversity, and we can also look at the relationship between size and structural virality. So just to give you a sense of the kinds of things that we see, and this is also really a validation of the metric itself. Up here, this is just a straight broadcast. So there's a single node, and then there's a huge number of retweets from this node. This is, I think this is CNN actually. And so the reason why it looks dark is there's just so many lines. There's like 10,000 nodes here. But essentially this is one layer deep. And then as you go to the right, you see things are getting, there are still big broadcasts here, but as you continue on from left to right and from top to bottom, you see that these structures are becoming deeper, the biggest broadcasts are becoming relatively smaller, and things are becoming more separate from each other. And what's interesting about this plot is that we didn't put them in this order. This is exactly the order in which they're ranked according to this Weiner index, right? So you can, I think, convince yourself that this index is capturing sort of roughly the intuition of what we mean when we talk about viral. And all of these different structures are represented in this collection of a few thousand observations that we have of very large events. What's also interesting is that it's very unusual to see a plot like this, right? Normally you're trying to sort of, make things go on the diagonal. This is about as far from that as you can get. That on the x-axis we have the size, the rank of the size, right, of these. All of these are big events, by the way. So we're restricting our attention to large events. And so we rank everything from big to small. And we also rank everything in terms of its structural virality. And you can see that there's essentially no relationship between these two. So to put it another way, if I tell you that something is really big, you really have no idea how it got big. Right? It could have gotten big through a sort of multi-generational process of viral spread. It could have gotten really big from a single broadcast. You really have no idea. And finally, because we were sort of mystified about this seemed like something that was inconsistent with the standard models. But actually, it turns out it's not. That even a sort of very, very simple model where we just assume a branching process where at every node, you just draw from a log normal distribution with some standard deviation and some mean offspring, that you can, in fact, get this very low correlation. So what's going on here? In fact, the correlation we see is about 0.2 in the data. So we're sort of imagining things are in this region here. Well, let's just, the different colored lines correspond to log normal distributions with different standard deviations. So that actually doesn't seem to matter too much once you get past a standard deviation of 1. These other curves are pretty similar. But what's more interesting to me is that you do see these low correlations between size and structural virality, but you only see them when the mean number of offspring is well below 1. So why is that interesting? Because 1 is the epidemic threshold. Sort of, if you're familiar with this literature, R0 is this the reproduction rate, the basic reproduction rate, is what epidemiologists tend to focus on, and they always want to keep R0 below 1 because once it gets bigger than 1, that's when you see exponential growth. So the assumption is that viral things only happen when this reproduction number gets bigger than 1. But it turns out that everything we're seeing is consistent with a model where R0 is well below 1. Right? So even things that are viral aren't really viral in the sense of these models. But because they're starting out, well, actually really just because on a network like Twitter you have such huge variance in the number of followers that people have, you can actually see these patterns that look extremely viral without assuming anything about the, while keeping your model in the subcritical regime. Okay, so yes, that really just summarizes what I said. We have a huge amount of diversity. The structural measures that we have constructed seem to do a pretty good job of capturing this intuitive notion of viral. We see very little correlation between size and virality, which was very surprising to us. And then, having seen that, we were then surprised again to find that we could actually recreate this result with an extremely simple model, as long as we kept it in this subcritical regime. So what does this mean? So I would say that this is actually an example where it really is important that you have a huge amount of data. That when you are studying these rare events, where sort of 1 in sort of several thousand events is sort of in your ballpark, and then you want thousands and thousands of these events to study, you need many, many millions of observations. You really do need a huge amount of data to even be able to ask questions like this. But it's not just a matter of sort of putting the data up there and looking at it. There really is, I think, a new theoretical insight here, that there's this very large literature of, that's theoretical of modeling these processes that we can imagine in our heads. And yet it turns out that much of what we're seeing, or pretty much everything that we're seeing, is consistent with a regime in these models that really nobody studies. Right? That everybody is interested in the critical threshold because that's where all the fun stuff happens. And nobody really sort of worries about what happens in the subcritical regime because nothing's happening. But actually a lot is happening. And so I think that this sort of points us in new directions for theory as well as possibly in practice. And finally, I'd say this is a nice example of what Sherrod likes to call computational social science, which is really this sort of sweet spot between answering or asking interesting scientific questions, but also requiring sort of very serious computer science skills. So this is sort of in this kind of emerging intersection between social and computer science, and it's something that we would certainly like to encourage more of. So, okay. So that's observational data. That's what I want to talk about there. I also want to talk about, as I mentioned, experimental data. And here we have a rather sort of different set of pros and cons and a rather different set of issues. The nice thing about experimental data is it really addresses the primary deficiencies of observational data, which is you can get a very good handle on cause and effect. You can also, because you're designing the experiment yourself, you can really ask the question that you want to ask, rather than just picking up a boatload of data and trying to figure out what your question is. And you can deal with a lot of these privacy concerns more elegantly simply by using standard human subjects protocols and allowing people to opt in. Of course, the problem is that any experiment that's simple enough for us to actually understand is probably ridiculous in terms of the real world. So you always have this concern about external validity, that yes, you've demonstrated cause and effect, but of what? Some abstract game that isn't anything like anybody actually plays. So that's certainly a challenge for experiments. It's also a lot more expensive to run these kinds of things. It's, you can't really, at least not so far, we can't run experiments with hundreds of millions of people. So the scale of experiments is usually much, much smaller. And of course, there's sort of typically not even any attempt to generate a representative sample of the population, although that may or may not be a problem. Finally, there are sort of deep disagreements between different disciplines. I'm thinking economics and psychology about whether it's okay to trick people while you're doing behavioral experiments, and the psychologists think that it's fine as long as you're sort of sensible about it, and the economists are generally adamantly opposed to any kind of deception at all. So there's some questions there about whether that limits your the kinds of things that you can do. Just sort of historically, I would say I look back to 1969 when Morris Zeldich, the sociologist, wrote this very interesting paper called "Can You Study an Army in a Lab?" And he was asking the question about the sort of big data question of the day, which was can you put sort of if you're interested, sociologists are interested in these sort of macro sociological phenomena, can you actually just do them in laboratory settings? And he said, well, clearly it's not possible from a practical point of view, but he also went on to argue that it wasn't really the point, that in fact, because experiments were designed to test theories, you could test theories of social action with small groups, and then you could use the theories to scale up to the kinds of sizes that we consider in real life. I would say, looking back, with the benefit of hindsight, that Zeldich was certainly right about the practicality, but he was wrong about the necessity. And I'll go back to this point about the micro-macro problem, that we were interested in these, precisely what's interesting to us about social phenomena is the way in which they go from small to large. And so unless we are able to test theories about emergence directly, i.e. with experiments, then we're probably not going to be able to solve this problem. And once again, this is, fast forwarding 40 years, it seems increasingly possible to do what Zeldich had ruled out, which is potentially study very large groups of individuals in a lab setting. So this is something that I've been thinking about for about a decade now, and I'll just very quickly mention a couple of early experiments back when I was at Columbia. One that was done with Peter Dodds and Robbie Mohammed, where we replicated Stanley Milgram's famous small world experiment. I'm sure you all know about this experiment, so I won't go into any details, but you might recall that Milgram had about 300 people trying to get paper packets to a single individual target person, and that was how he discovered the famous 6 degrees of separation. We were able to replicate this using email on a much, much larger scale, where we had 18 different targets in 13 different countries around the world, and about 24,000 chains trying to reach them. And these chains passed through about 60,000 participants in over 160 countries. So, the results were surprisingly consistent with Milgram's, which was great. But the other thing that we learned in the course of running this experiment or that we discovered in the course of this experiment was what my friend Jonah Peretti calls the bored at work network, which is this vast network of people sitting around the world at their computers at work, and they're bored. And if you can, if you can get them, if you can give them something sort of interesting to do, and it can be, LOL cats or, or funny videos, or it can be, it can be social science, as long as it's somewhat entertaining. And remember, they're bored, so the threshold is not that high. You can get them to do social science for you. So we were inspired by this, and we went on to do another experiment with Matt's Organic, who's now at Princeton, where we looked at social influence in decision making, and we did this in the context of music, where we got about 14,000 people to make choices between 48 different songs by unknown bands. And some of them just got to see the names of the bands and the songs, and others got to also see how many times these songs had been downloaded by previous participants. So there was a social signal involved in that condition. And so what we found is that when people know what other people like, popular things become more popular and unpopular things become less popular, but at the same time it becomes increasingly difficult to predict which things are going to become popular. And we were able to measure this unpredictability directly simply by replicating these worlds, this experiment many times. And so this gave us some real insight into the process by which cultural hits become hits. It also, I think, cast some doubt on the idea of revealed preferences, that markets, that preferences are sort of things that people have in their heads that are handed to them as exogenously, and markets simply reveal these preferences. In fact, markets where social influence is present actively construct the preferences as they go. So, so these were both, sort of, to us, very exciting experiments with pretty large numbers of people by experimental standards. The problem is that they're really hard to do, these experiments, and they take a lot of time. In both cases, several months of programming up front, and they both relied on what we call the field of dreams principle, that you build the experiment and then you hope that the board at work network shows up, and if they don't show up, then you're in trouble, right? And then you put several months down the drain. Of course, you also have this problem that the people who show up are probably wildly unlike everybody else, and so you have to sort of keep that in mind. So basically, what we wanted on the aftermath of these experiments was to find a more replicable, reliable, and flexible solution for running experiments. And as it happened, or rather as it happened, right around that time, Amazon created this wonderful site called Mechanical Turk, which they created as a crowdsourcing site. And initially they were just using it internally to clean up their own web pages. And by crowdsourcing, I mean anyone can go to this site and put up a job, typically image labeling or some sort of sentiment analysis. I'm sure many people in this room have used Mechanical Turk to classify various things. We began to view it less as a way of getting work done than as the 21st century equivalent of putting flyers up around campus. So, back in the old days, and actually still today, psychologists will, advertise on campus and recruit students to come and participate in some experiment on learning, and come to the psych lab at 3 o'clock on a Friday afternoon. We'll pay you $10 for an hour of your time. And really, this is just the same thing. We're able to recruit people and pay them all through Amazon's platform, except now we can do it on a global scale at 24 hours a day and for a much lower cost. So the first experiment that we ran, this is work with Winter Mason back when he was at Yahoo. He's now at Stevens Institute of Technology. Was a very simple experiment just to really kind of demonstrate that this could be done, looking at the relationship between financial incentives and performance, because after all, this was a crowdsourcing website and nobody really knew how much to pay people. So we did this very simple experiment where we gave people a set of images. In this case, it's images of moving traffic taken from a traffic camera. There's a wonderful website called trafficland.com, which has live streaming video from traffic cameras all over the world. It's another great way to waste time. highly recommend it. This is a camera in Maryland, which is where Winter is from. And so we take these images at 2-second intervals, and then we randomly shuffle them. But of course, we have the timestamps, so we know exactly what order they go in. And then we make the participants put them back in the right order. We got about 600 participants. We ran this experiment over a period of a couple of days. They sorted 36,000 sets of images. What they didn't know is that different people got assigned to different conditions. So in some conditions, you saw 2 images. In other conditions, you saw 3 images like you do here. In other conditions still, you saw 4 images. So we're increasing the difficulty of this task by increasing the number of images. And we also paid them at very different levels. So we might pay them 1 cent per task, or 5 cents per task, or 10 cents per task, right? So a pretty order of magnitude difference in pay. So what difference does the pay make? Well, on the left-hand side, you see how much work they did. And you can see that as you pay them more, they do more work, which is what you would expect. They sort more images, and also the easier the task is, the more images they sort. Right? So they could do anywhere from 0 sets of images to 99 sets of images. So there's a pretty wide range in what's possible, and you can see these very nice upward sloping curves here. If you look at the right-hand side, however, the accuracy does not change with pay rate at all. Right? No, absolutely no effect. And in fact, if you take out the base rate, because it's easier to randomly guess the order of 2 images than it is 3 images and 4 images, the difficulty doesn't have any effect either. So basically, people do have the same accuracy no matter what. So what's going on here? Well, afterwards, we asked them in an exit survey how much they thought they should have gotten paid to do what they just did. And you'll see there's a beautiful linear relationship up here that this is what they were paid to do for the work. This is what they thought they should have been paid to do for the work. So people who got paid 1 cent per task thought they should have gotten paid 5 cents per task. The people who actually got paid 5 cents per task thought they should have gotten paid 8 cents per task. And the people who got paid 10 cents per task thought they should have gotten paid 13 cents per task. This effect was pretty robust. We looked at a different experiment as well. We found the same result. Now, the message for crowdsourcing is maybe not one you want to hear, but actually the lesson is you pay people as little as possible, because you're not going to get any benefit from being nice. So there's been a huge amount of work done since then on Mechanical Turk. It's become very popular with behavioral scientists. Lots of classical psych experiments have been replicated. Things that have been done in the lab for many years, they can do them online now, and they get exactly the same results, which is great. There are guides for running AMT experiments. Winter and Sid Suri, who I'll talk about in a second, are sort of 2 of the world experts in running experiments on Mechanical Turk. And basically, the advantages in speed and cost are enormous. But most of these experiments, including the one I just described, are really sort of studying behavior at the individual level. This is sort of a standard, this is really familiar from standard psychology experiments. But of course, my whole motivation for doing these experiments is to try to understand this micro-macro link. We want to be able to do experiments where we have lots of people participating at the same time, and preferably have them connected in some sort of network. And this presents a tricky problem in that you need everybody to sort of show up at the same time and stick around for the duration of the experiment. Now, this is something that Michael Kearns at Penn has solved very nicely in a sort of groundbreaking series of experiments over the last decade, where they conduct experiments in a lab. And they, a couple of times a year, they'll bring students into the lab, and they have 36 machines in the lab, so they do, N is always 36. And they have studied graph coloring and consensus games and economic exchange and more recently, I think, network formation. But I know Michael very well, and I've talked to him a lot about these experiments, and I know how difficult and painstaking and expensive they are to run. So this is something that you can do every 6 months. It's not something you can do every 6 hours. So what we would like to be able to do is run possibly larger experiments, but also more cheaply and faster. So to do this, Sid and I developed a relatively simple trick, but it works surprisingly well, is that you can't actually initially get, if you just put a hit up on Mechanical Turk, you won't get 50 people to show up within a couple of minutes, but you might get 4 people to show up in a couple of minutes. And so you run a series of small experiments, and then at the end of the experiment, you ask people, would you like to play this again? If they say yes, and in fact, they almost always say yes, then we just add them to a list, and then we build up over a couple of weeks, we build up a panel of maybe a couple of hundred people, and then we just recruit from this panel. So we'll email them the night before, and we'll say, we're running experiments at the following times tomorrow, please show up. We can ping them again a couple of minutes beforehand, and then they sit in a waiting room, and the clock counts down to, or the counter counts down to 0, and then the game begins. Now, we've used this approach in 3 different series of experiments. I'm running out of time a little bit, so I'll try to talk about a couple of them. The first one is work done with Sid, where we studied a linear public goods game. So this is a very commonly studied model of cooperation. It runs for a series of rounds. Each member in a group is given, on each round, is given some endowment, usually some points which are convertible to cash at the end of the game. Each round you get asked to give some of this endowment to a common pool, and you can give 0 or you can give the whole amount. This is the common pool is then summed up and multiplied by a constant factor which is greater than 1, hence the linear public goods, and then it's redistributed evenly to all members. So this is critical that regardless of what you put in, everybody gets the same amount distributed from the pot. So this is where the dilemma arises, and this is why people study this game so much, is that the social welfare maximizing solution is where everybody puts in the maximum amount, because then everybody gets the maximum amount multiplied. Of course, or however, as an individual, the best result you can get is if everybody else puts in the maximum amount and you put in nothing, right? So you want a free ride, selfishly, you want a free ride on the contributions of others. Of course, if everybody thinks this way, it's just what your mother said, then everyone will be worse off. And so, hence the dilemma. So the question is, the question that we're interested in is, how does this change when you put people on networks? And we believed going into these experiments that the structure of the network should probably affect the outcome, and there are a couple of reasons for that. One is that it's well known, and this has been demonstrated through many experiments, that people are what are called conditional cooperators. There are a small number of people who are sort of unconditional cooperators who always do the right thing no matter what. There are a small number of people who are unconditional defectors who always do the wrong thing no matter what. And then everybody else is sort of in the middle, where you kind of look around, and if other people are doing the right thing, you're inclined to do so as well, but you don't like to get taken advantage of. It's sort of, when everybody is dividing the tip at dinner, or dividing the check rather, after dinner, everybody sort of wants to put in their fair share, but more than that, you don't want to be the one who overpays. So this is the notion of conditional cooperation, and the idea is that when conditional cooperators are allowed to, or when cooperators are allowed to interact preferentially and exclude defectors, they can reinforce each other and good behavior should proliferate. The other notion that's relevant is that cooperation might be contagious, that you doing the right thing may prompt somebody else to do the right thing, which then prompts someone else to do the right thing. And for both these reasons, you would expect that network structure should matter. There's some very kind of fluffy supporting evidence for this, but enough that it encouraged us to believe that there was something there to find. So we ran these experiments on a selection of networks. So we created 6 different types of networks, ranging from highly clustered networks where everyone is playing with the same set of people, and these cliques are separated from each other, all the way to essentially a random network where none of your neighbors are neighbors of each other. And the hypothesis is that cooperation should be higher in networks that look like this than in this. Unfortunately, that didn't turn out to be the case. there was really no difference at all between contributions in these networks. And so this is the raw data here. You can see that all these curves are essentially running parallel to each other, and that the main difference is that they start off at different points. Now this, of course, is just a random effect. People don't have any experience in the network, so what they contribute on the first round has nothing to do with the network. So if you net that out by normalizing them all at the same initial contribution, you can see that these curves are extremely similar, and all these error bars are overlapping. So this was very disappointing to us and somewhat puzzling, because there is this intuition, which you keep wanting to have, that says, well, if you allow good people to interact with other good people, then they'll keep being good. And they should do so more than if they are forced to interact with bad people. So possibly the problem is that these networks were static. So the thing that we missed is that in the real world, you have this extra degree of freedom, which is that if somebody is doing something you don't like, you can simply stop being friends with them. And then you can go off and find somebody who you think is a better prospect. And so what we wanted to do is capture this notion of tie updating or dynamic networks. And again, there's some previous evidence that this should work. But actually, the effects in these previous studies were extremely small. And what was interesting about them is that even though the ties were being updated, the individuals in the experiments were not actually given the ability to choose who they wanted to interact with, or even to refuse links from other people. So you can imagine if you can't do that, then what's to prevent a malfeasant individual from forcing themselves upon you? So in work that was done last year with Sid and also Jing Wang, who's a grad student at NYU and a former intern of ours, we then studied a related game. For various technical reasons, we studied a prisoner's dilemma rather than the public goods game. And we started off in the same way. You have a particular kind of network that you're allocated to, but now after every R rounds, you get to make K updates. So there's two parameters here that govern the update rate: how frequently you get to make updates and how many updates you get to make. And each update, you either get to delete an edge from someone you don't like, or you get to propose an edge to someone else. Now, if you do propose an edge to someone else, they have to accept that proposal for the link to be created. And so you have an incentive not to propose links that you think will be refused. So by studying different values, 3 different values of R and K, we're able to study a wide range of effective update rates. We also looked at 2 different initial substrates, and we looked at static networks as control. So again, we have a large number of experiments. We want to do 4 different realizations of each condition so that we can do some averaging. So we're looking at about 88 experiments in total. So what do we find? Finally, we get a result. We see a dramatic increase. Interestingly, even at the beginning, right? So just knowing that people can do this automatically changes everybody's behavior. So it's simply the anticipation that if you do the wrong thing, people will cut links with you. It has a tremendous sort of self-policing effect. Secondly, this cooperation persists for quite some time, and then crashes towards the end because people realize that the game is a finite game, and so they're trying to take advantage of, or at least not get taken advantage of. So on the right-hand side, you can see this is for all values of the updating rate, and you can see that so this is sort of converting the R and K parameters into a total number of updates per player over the course of the entire game, and you can see that even for pretty low update rates, so this point here is just 1 update every round, right? So it's not a huge number of updates. You're generating a very large effect, after which subsequent increases don't have much effect. So what do we learn? Well, static network structure doesn't impact cooperation, but allowing individuals to update ties does. And even a low rate of rewiring is enough to have a big effect, as long as you let players choose or refuse partners. Okay. So what do we mean by big data here? Well, you know, we certainly are interested in scaling these experiments up. And we can imagine if we, instead of having 100 people in our panel, we had 100,000 people or 1 million people in our panel, we could conceivably study much, much larger networks. But I think what's even more exciting than that is our ability to run so many experiments over a relatively short period of time. This really allows us to explore a much wider parameter space than would have been you know, feasible in a traditional lab experiment. And if you're familiar with the, you know, with the behavioral economics literature, you know, the sort of interval between, you know, one experiment and the next experiment is roughly a year, right? So you run a set of experiments and then you get your results and you write up your paper and then you think, we really should have tried this variation. And so then you apply for another grant and you get your, you know, you plan your experiments and you book your lab and you get your students to come in and then you write your results up and then, you know, a year has passed. So imagine you could shrink a year to an hour, right? Imagine you could say, well, you know, we had a new idea, let's run those experiments this afternoon and then let's run more tomorrow. The amount of exploration that could be done would be, you know, qualitatively different. And I think that that has pretty profound implications for what we can do in terms of experimental social science. And finally, if we can set up these subject pools, and this is something we're actively working on now, but we haven't succeeded in doing yet, imagine we can keep these people around for a year or more, rather than going out and recruiting a fresh batch of them every time. Over time, you could learn a lot about how people play different types of games. You could say, oh, well, I want to run a cooperation game, but I only want to sample people who have played generously in previous games. So if I put generous people together with other generous people, do they remain generous or do they revert to the mean? You know, I can sample people on demographic variables. I could even sample them based on how they had played other types of games, right? So if we have a learning problem, you know, how do people who played a particular way in a collaborative learning problem, how do they play in a cooperation game? So there's sort of actually new types of questions that we can begin to ask simply because we can have these large persistent panels. And none of this is big in the sense that it requires computational data. I think it has big implications. It's big by the standards of historical experiments, but it's not big data. It's not hundreds of millions of observations. So in addition to the things that I've talked about, and I really am running out of time now, so I'll just skip over this, there's other kinds of studies as well, and they have their own pros and cons. Some really great work going on at Facebook, and also my colleagues at Yahoo on very large-scale randomized field experiments to study ad effectiveness and social influence, and just a couple of weeks ago, voting turnout. Survey research is also changing with the web. Matt Selganic, my former student at Princeton, has developed this whole scheme of what he calls wiki surveys that allow respondents to actually introduce new questions into the survey as well as voting on existing questions. So this combines the efficiencies of survey methodology with the flexibility of interviews. And finally, something that I think we really have not succeeded at doing yet or even have any good ideas for how to do but would love to do is trying to sort of combine the strengths of ethnographic methods. So this is really small data. This is, you know, going out into the field and actually talking to people, which is not something I would ever do. But I have colleagues who do that, and they learn things that we can't learn, right, from looking at mouse clicks or search queries. They actually can extract knowledge that resides in people's heads, and they can see what they're doing in the field. And wouldn't it be wonderful if we could calibrate this sort of big but thin data that we get from online sources with the small but rich data that we can get from an actual field setting. So I think there's lots of, you know, sort of an amazing number of directions to go. And I just want to sort of finish by reminding everybody that you know, all of these different approaches have their strengths and weaknesses. In some cases, as I've mentioned, the size really does matter. If you're trying to estimate a very, very small effect size, and this was demonstrated by the voting study that was published in Nature a couple of weeks ago. You know, you're talking about like a 0.4% increase as a result of some treatment. Like, you know, you need millions of observations to even be able to estimate that with any sort of statistical significance. If you're observing rare events, things that are 1 in a million events, you need millions and millions of observations. But in lots of other cases, the size is not that important, and other kinds of considerations dominate, either the quality of the data or the speed of obtaining it, or the speed at which you can run experiments. And ideally, I think what we need to figure out, and a big challenge for the near future, is how to coordinate these sort of really sort of multi-methodological studies. How do we take the advantages of experiments, lab experiments, field experiments, observational studies, and even ethnographic studies, and approach the same problem from lots of different perspectives? I think that's when we're really going to start making progress. Thank you.